Okay. Thank you for coming to my talk. Thank you for giving me the opportunity to introduce my Bluetooth library to you, named Bluetoe. My name is Torsten Robitzki. I'm a freelancing C++ embedded software developer. Whom of you is familiar with Bluetooth Low Energy? Okay, more than half of it, I would say. Mostly peripherals, I guess? No? Someone building peripherals? Which stack?
Nordic.
Nordic, okay. And you?
Nordic.
Ah, okay. So, this is Bluetooth. On the left side, we have a wristwatch, maybe as a peripheral measuring our heartbeat, for example. On the right side, we have a smartphone called a controller, collecting and displaying our heartbeat. Usually an unconnected peripheral sends out so-called advertisement. With this advertisement, this peripheral announces its provided services and connection details. This allows the controller to establish a connection to this peripheral. So after both devices connected, we have a classical server-client architecture. But this time, the smaller device is the server, and the bigger device is the client. More concrete, this is an attribute server. The server serves attributes. So what are attributes? This is how an example attribute table could look like. An attribute table will always have these 4 columns. The first row is the handle. A handle uniquely identifies an attribute at the protocol layer. So if later on the protocol layer you want to identify an attribute, you just send the handle of the attribute. Handles are always 16-bit in size, no matter how large the characteristic data or something like this is. The next column is the type. This is an UUID, typical 16-bit UUID, but there are occasions where you have 128-bit UUIDs. These types identify how you have to interpret the data in the third column. And for a typical attribute table, most of all attributes have a type UUID that is just 16-bit long. The data column is data of arbitrary length and have to be interpreted with the type, the second column in mind. The second column defines how you interpret this data. The fourth column is read and write permissions, and these permissions are usually defined on the higher layer of the protocol, not on the attribute protocol layer. So to read and write protocol data attributes from the attribute server, we have a protocol. This allows us to read attributes, to write attributes, and to find or read sets of attributes. And there's another direction from the server to the client to send data. This are called notifications or indications, and are usually sent if data in an attribute has been changed. So, congratulations. Now you are recognized attribute protocol experts already. So on top of attribute layer protocol, there's another protocol called the generic attribute profile. GET arranges data into characteristics and groups characteristics into services. Services are the yellow boxes, the blue boxes, and characteristics are the yellow boxes. So this server serves 2 services. The first service has 1 characteristic. The second service has 2 characteristics. A characteristic will always have a value and will always have a set of properties. An attribute can have additional metadata, like on the left side, the client configuration and the user description are so-called descriptors. And the properties of a characteristic defines the set of allowed operations. Can I read the characteristic? Can I write it to it? Basically this. Services and characteristics both are identified by UUIDs, again, either by a 16-bit UUID or by a 128-bit UUID. The 16-bit UUIDs are defined by the Bluetooth special interest group, so they are predefined. If you want to make up your own services and characteristics, you can always use 28-bit UUIDs. So in this structure, GATT structure, this combination of services and characteristics maps into an attribute table. This is a connection to the protocol I showed you before. The red boxes shows attributes where the handles, types, UUIDs, and values. All of them are defined or encoded in attributes. So we have, in this example, an attribute server with 10 different attributes. A characteristic value is a single attribute with characteristic UUID as type. These are the attributes with the handles 3.8 and A. So the smallest possible characteristic will always contain 2 attributes, and thus the smallest possible attribute server or GATT server will always contain at least 3 attributes. So the protocol based on the GET protocol is basically just grouping attribute protocol sequences into so-called procedures, and then you basically have the functions to discover all the services and characteristics on your GATT server, then read and write to characteristics, read to and write to descriptors, and to receive notifications and indications from the server if characteristic value changes. So that's basically all I want to say for the Bluetooth protocol. I think that's enough to show you my library. So I started to build Bluetooth peripherals by using existing C libraries, SDKs, namely from Nordic and from Texas Instruments. And while I was working with this SDK, I was surprised by the complexity to get even the easiest thing done. I don't know if you would agree. Yes? Okay. And I thought of how would I like to use a Bluetooth low energy library. And I think basically I would love to see a library that makes easy things easy, at least makes the easy things easy. The complicated things could be complicated, but the easy things should be easy. Because I would like to have something running up very quickly, because this gives me a flatter learning curve, and I could easily better explore libraries if I get easy things done first and easy. So here's a nearly complete example of a Bluetooth GATT server. Only the required includes are left out, and the implementation of 2 functions. These 2, one is to set an I/O pin, the second is to initialize the hardware for the pin. The name of the example in this, you will find this in the source of Bluetooth. The name of this example is Blinky. And this example allows a connected GATT client to remotely set an I/O pin by writing to the one and only characteristic of the provided service. So this type defines the whole GUT service. It's just a type, and it entirely defines how the GUT structure of the server looks like, and this is even the same way this is how the attribute table is defined. This implies connections to how to write characteristic values, and we have a link layer that's a layer below or somewhere below the GUT table, and this will not be a part of this presentation. So this is a pretty small code size, I think. And to achieve this, the way is to just apply useful defaults for things we want not to decide yet, but later maybe. So, for example, this server already, we have defined a server with a service with a certain UUID, and by default the server would advertise this service in its advertising data. So there's no need to add this to your advertising data. The characteristic has no defined UUID because the library will generate a UUID for you based on the UUID of the service if the service has a 128-bit UUID. Bluetoe will extract the properties from how you define your characteristic value. Here we have just a mean to write to the characteristic, so apparently the properties of the characteristic is right, nothing more. You cannot read from it. You will receive an error if you try to read from it. Bluetoe can anticipate the range of valid values to a characteristic value. In this case, we have a Boolean value, and every attempt of a client to write anything except a single byte, this is either 0 or 1, will fail, and the client will receive an error from the library. And by default, the server starts advertising, so there's no need to look up how the function is named that you need to call to goddamn let your server advertise. And last but not least, a Bluetooth server will just handle connections. They will accept connections for you. So there's no need to do anything special, just to accept connections from a client. So next design choice is to prevent error sources by design. As shown on the last slide, there's much less code to write, and lesser code means simply lesser ways to make errors. Here's another example. This time, this is a server that notifies button presses. A client can connect to this server and can subscribe to the characteristic, and then will receive notification once you press the button. The function notify just queues the information. This is an example how this library by design prevents certain error cases, and this is one way. The notify function doesn't queue any PDUs to send out on the link layer, but just queues a single bit that says this characteristic wants to be sent out as a notification. And once there is enough room on the lower link layer, the link layer calls the library to ask what is the value of this characteristic. So there's no need to check for errors if you call notify, because this function can simply not fail. It just flips a bit. And a last point here is the UUID I want to if I have more than one characteristic that can be notified, I certainly have to identify the characteristic I want to notify. And this I do by giving the UUID as the compile time argument, and the library will check if this characteristic is even configured for notification. If it's not notification, you will receive an error at compile time. So this one thing I like is function that cannot cause an error have a function type of void, not an integer that sometimes in the future may return an error, but now it will not. So this would be a completely change of an interface. If you change a function from it can return an error to a function that I cannot return an error, and vice versa. The attribute table is built at compile time, so you don't have to call a bunch of functions at startup that you have to check the errors from. So there is simply no code you have to write to build an attribute table, and this can simply not fail. Yeah, and as I have shown in the previous example, a lot of error handling can be done by the library if you give the library enough information to do so. And you can even check a lot of errors at compile time with this approach. So the next principle would be to use as little resources as possible, as resources are expensive by default. The first one, no heap. The set of library functions that implement your heap usually is quite large already. The library tries to use a lot of C++ so-called zero-cost abstractions. We will see some examples of that in a few minutes. And it will favor ROM over RAM. So if there is any chance to store the same information in ROM, so please store it there. And you don't have to pay for unused features. This means there will not be a bunch of callback function pointers that most of them contain 0, and you have to check them for if they are not 0, then call this function. Yeah. And now I want to show you an incomplete set of the features of Bluetoe. And Bluetoe only implements the GATT server part of the GATT protocol. Bluetoe is not a client, just a server. So the general structure of a GATT server declaration looks like this. All relevant information to build the server attribute table is encoded in a single type. Here's a type alias named GATT server. There's always one server in your GATT attribute server containing one or more services, and each service should at least contain one or more characteristics. So the general structure of an application is we have some includes. If you like to shortcut the Bluetoe namespace, feel free to do so. We have this one server type. We have an instance of this type called server here. We have this lower layer, and we have some mean to give CPU to the library. So now the first feature I want to show to you is encryption. This is a very recent feature, just finished a few weeks ago. Currently just works pairing is implemented, and Bluetoe has currently no support for bonding. Encryption requirements can be defined on a server level, so this defines every characteristic on the server would by default require encryption to be readable or writable, otherwise the library would respond with an error. You can override this on the server, on the service level, and you can even finally override this on a per characteristic level. So next, some means to define at runtime how our characteristic values look like. Here, this is a set of how to provide a characteristic with a constant and read-only value. This is just a characteristic that would have a size of 4 bytes and will provide this constant value. This would be a string, and this finally just a bunch of constant data with arbitrary size. Bluetoe has bindings to global variables, which could be quite handy for small examples. The first characteristic is bind to this value, so if you read from this characteristic, you will receive the value of the variable. If you write to the characteristic the variable will receive the written value. We can remove, or maybe the first characteristic will have the attributes read and write, and we can remove the write property or the read property. So the variable is technical read and write, but we could restrict the access to this variable by removing either the read or the write property from the set of properties for this characteristic. We can use free functions. So in case that the function is written, we have a read handler. This handler is called with a buffer, with a buffer size, and we can then fill the provided size. And we can have a handler to accept newly written characteristic values. The same can be applied to object. This looks like quite similar. We have a mean to read, we have a mean to write. With member functions, there's the need to have an instance when calling the handler at runtime. That instance has to be passed to the library by reference. So we have an instance, and we have to pass the instance to the library. So if the call is made, we have an instance to call it on. So notifications indications is a feature of Bluetoe. To implement a characteristic with notification or indication, there have to be some mean to define the value of the characteristic. This is, again, this read handlers. Adding a read handler and a notify or indicate property to the characteristic is all that is needed to enable a characteristic for notifications or indications. So just this is required. And again, here we can just remove the read access again. So the second characteristic will just have the property to be indicated, but you cannot read from it. This shows how we would queue an indication or notification. This server serves the service from the last slide. This is this one here. So we have a service that looks like this. And then we have this function to queue a notification. Remember, queuing a notification means just setting one bit, so there's nothing that can go wrong. And again, queue indications. So that is a short overview of the features, of the gut features of the library. There are other means to bind values. There are support for control points, for example. There are means to configure your advertising data. There are means to configure your link layer. But that should be a small overview of the library and how to use it. So here are some numbers, some examples included in the Bluetooth sources, and their Yes.
When does that return?
This one function returns once in a while, and there is a function that you can call to force this function to return. This is safe to be called from interrupt handlers, for example. So if you have something that you want to communicate to the main thread, you could call this function, and then from within an interrupt handler, and then this one function would return.
My question essentially is, very often you don't have only Bluetooth, but you have other things to do.
Yeah, sure.
So would you put this one in a special thread that only runs in Bluetooth and all the other things are in other threads, or just do you call this function once in a while?
It's a model if you have other requirements to use Bluetooth in other environments. We could talk about how to provide CPU to the library. This is currently the only way, and for at least some examples, this works quite well. I don't like RTOSes in any kind because, yeah, I think it's a waste of resources. So I wouldn't run this in a thread, but it might work, yes.
Well, that would be exactly my next question. So
it wouldn't.
Notify from a different thread. Well, bits switching from different threads is a dangerous thing.
There are some functions that are safe to be called from an interrupt context. One function is to kick out this loop, this one function, so that the one function will return. The other functions that are safe to be called from an interrupt context are notify and indicate, because they are simply setting a bits. So, and it's handy.
If you set two different bits from two different interrupters.
Currently, this is just working on single core, and even just on one core of many, and so, yeah. Does this answer your question? Yeah. So, these are the binary sizes of the example. Blinky is the first example that we saw first, 15K of flash. The second one is the same example without encryption. It's 13 and 70K for a complete bootloader implementation that you also can find in the sources of Bluetooth. For comparison, this 88K is a BLE stack from the vendor of the chip I'm using, the NF52 or 51. So that is the lower limit for any application if you use their SDK.
You replace the S110 with your Bluetooth B?
Yes, exactly. There's no need to use a soft device. Everything that is implemented in the soft device is implemented by Bluetooth. The comparison might be quite unfair because apparently I think Bluetooth will have less features than the SDK provided by Nordic. But if you just need something like a bootloader, for example, you might be considering Bluetooth because, yeah. Yeah, this is the last part of my presentation. So how are these small binary sizes possible? To be honestly, I don't know. I just wrote it and it ended up this way. I think I've just skipped almost everything that I think would add overhead that is unnecessary. So here are some examples of the design choices that I made and that might add up to this. This is a rough sketch of the Bluetooth server class that we saw in the examples before. This has mainly two functions. The first function receives input from the lower layer. This is an L2 cup layer. It parses the attribute protocol request and will assemble the response to the client. The second function gives access to the attribute table. So basically the first function implements the attribute protocol in terms of the second. The attribute protocol is used to access the attribute table. So we have two functions, one for the protocol, the second for the attribute table. This is a sketch of how the internal representation of an attribute table looks like. This is just a pair or tuple of two values. One is the 16-bit UUID. If you remember, the most of the attribute tables UUIDs are 16-bit. So we have just the design choice is to implement the 99% or the 80% and then make some hacks for the other 20%. And we have a second function. Remember, that's a function that implements access to the value of the attribute. That is just a function pointer. And the library will generate functions based on what you decided how your attribute or get table looks like. And these attributes are stored completely in ROM. This are tiny arrays per characteristic, and you can easily look up which characteristic, which handle belongs to which characteristic. A next implementation details, just an example, is this is just an example of a feature where you don't have to pay for what you don't want to use. Namely, long writes. Long writes is a feature in BLE that allows you to write to a characteristic value in multiple small steps. These steps are stored on the server until you decide to commit all the small writes. So you have to configure a queue if you want to use this feature. This is the statement in the declaration of the server. Here again, a sketch of the Bluetooth server. This time with another detail. The server will derive from a write queue class with a single template argument here. This find by meter type is a template meta type programming function that will return either the shared write queue that we have shown in the example before, or if this is not given, it will return the type no such type. It's some kind of generic null used in Bluetooth. So finally, Bluetooth will inherit from one of these template specialization, either this one or this one. In the first case, the server will inherit all required buffers and bookkeeping structures, data. And in the second case, if you don't give this configuration option, the server will simply inherit from an empty base class, which all compilers are required to rule out. So that's it. That's the current state of Bluetooth is that what I've shown you requires a so-called L2 cup layer. The only implementation that is shipped with Bluetooth is currently for the NRF 52. It started with a 51 and it shifted to 52. It's not qualified by Bluetooth. I use it for prototyping a lot, and I think it's fun to work with. So further directions of this is my personal wish list. Looks like differently maybe. would be an HCI binding for using Bluetooth on desktop hardware. So I could even prototype peripherals on my laptop. Bonding would be nice. LA secure connections would be cool. More supported hardware. I think I've got the design quite good to replace the underlying hardware, but until I didn't use it, implemented a second hardware, it's just guessing. Especially for the lower part, for the hardware near part, better testing would be very nice. Yeah, and pull requests are welcome. So if you're interested in Bluetooth, if you want to help or if you want to add something, you're welcome. Yes, thank you.